Hi guys, it's Mrs. Allison. Today we are going to look at two examples of applications of double integrals beyond what we've looked at with volume and then what we're going to look at next, which is surface area. We're going to look at a couple of physics applications. We're going to start with mass, center of mass, and then go on to electric charge. So, suppose you have a 2D region, R, that has a density function with this rho. This is the Greek letter rho, and it's spelled R-H-O. Rho of xy at each point xy. So we can define the mass of the region as being the double integral over the region of rho xy dA. So that would be our mass of the region. Now, we also have something called moments. Well, a moment about an axis it measures the tendency, it's a measure of tendency to cause the body to rotate about a specific point. So moments about an axis are defined by the product of the mass times the distance from the axis of rotation. So if we have a region R with a density function rho of xy, then the moment with respect to the x-axis, capital M, is the double integral over the region y rho of xy dA, and the moment with respect to the y-axis is double integral of x times the rho xy dA. And the center of mass can be found by dividing the moment by the mass, and the moment with respect to y divided by the mass is the x coordinate, and the moment with respect to the x divided by the mass is the y coordinate. Now, the center of mass is where the region will be perfectly balanced. Now, one of the phrases that you're going to hear that we're going to talk about is called a lamina. And a lamina, if we were to define it, is just a thin layer, a plate, usually of like rock or organic tissue or some other material, typically is what we defined that lamina by. So a plate or a layer or a thin layer, really thin layer. All right, let's look at an example of a problem. And what's interesting is in talking to Mr. Allison about this, he says he uses some of these concepts when he's doing 3D modeling in SolidWorks. He told me he would show me. I haven't looked at it just yet, but it's kind of interesting how closely what we're doing here ties into what he does. Even though he doesn't do the calculations, the SolidWorks program probably goes through these very calculations when it was programmed. So pretty interesting. So this question says, find the mass and the center of mass of the lamina that occupies the region D and has the given density function. Okay. What it tells us is D is the triangular region with the vertices 0, 0, 0, 2, and 1, 0. So I'm going to start and I'm actually going to sketch this region. So if we look at our region, we have 0, 0, 0, 2, and 1, 0. So we have a region that looks like this. I don't even think I'm going to be able to shade that. Okay, so we have this region that looks like this. Now, when we're defining our region is going to be our where we come up with our bounds of integration. So I need to determine if I'm doing this with respect to y or if I'm doing this with respect to x first. So am I doing dy dx or am I doing dx dy? I think on this one, I will probably choose to do dy dx, I think. So looking at dy dx, let's look at y. The lower bound of y would be 0. And the upper bound of y would be this function here. So that function is, the slope would be negative 2x plus 2. And then my x is from 0 to 1. All right. So if we look at the mass, and I'm going to find my mass first. It'd be nice to be able to leave that up for a minute. Well, you have yours to look at. Sorry, I don't have much room on the screen. So if I'm going to look at my mass, I'm going to set up the equation and I'm going to say the mass is going to equal the double integral over the region of, they gave us the row was x plus y, dA. Now the way I set mine up, I'm going to do the mass is going to be equal to the integral from 0 to 1. I'm going to do dx on the outside. And then 0 to negative 2x plus 2. And then this will be x plus y dy dx. Now this, remember with this iterated integral, we are going to head and deal with the integral with respect to y first. So we would have xy plus y squared over 2 evaluated from 0 to negative 2x plus 2. And then that would be inside the integral from 0 to 1 dx. Okay, so let's make our substitutions in. So my mass is x and y. Y we're going to replace with the negative 2x plus 2. So I'm just going to go ahead and multiply that. So we'd get negative 2x squared plus 2x plus negative 2x plus 2 squared over 2 minus all of that with 0 substituted in, but with 0 substituted in, that all just goes away. That part goes away. So I know my mass is the integral from 0 to 1 of, let's simplify this, negative 2x squared plus 2x. If I FOIL this together, I end up with positive 4x squared minus 8x plus 4. But I'm going to divide everything by 2. So I get positive 2x squared minus 4x plus 2 dx. So simplifying, that makes it nice. Simplifying this, we get negative 2x plus 2 dx. Now I'm going to integrate this. And integrating this, I'm going to get negative x squared plus 2x evaluated from 0 to 1, which tells me that my mass is equal to 1 when I make that substitution in. So we know our mass is equal to 1. And probably all of these should have said m equals. So we found our mass of this particular lamina that occupies that region. But now what we need to do is we need to find the moment with respect to the x-axis and the moment with respect to the y-axis, because that's going to allow us to find our center of mass, which is the next thing that we need to find. So let's start with our moment with respect to the x-axis. Doesn't actually matter which one you choose. So the moment with respect to the x-axis is the integral same bounds, but we're going to take and multiply y times that row function. Now what I want you to do is just hit pause and try this integration and see what you get for the moment with respect to x. Okay, again, I'm going to have to do my integration. It's going to be a little bit messy. So I get from 0 to negative 2x plus 2. Let's simplify this. So we get yx plus y squared dy dx. And I'm going to integrate with respect to y first. It is a slightly different function than what we did before, so I can't just use that. So I'm going to go up a degree. So we get xy squared over 2 plus y cubed over 3, evaluated from 0 to negative 2x plus 2, remember with respect to y. So substituting in with respect to y, we get a bit of a mess. Let's do x times negative 2x plus 2 squared over 2 plus negative 2x plus 2 to the third over 3 minus 0, that will all disappear, dx. Now, I'm going to take a bit of, let's go through here. I'm going to have to take some shortcuts, I think. If we look at this first one, I see that if all I had was this x here, this piece is the same as this piece. So I know it's going to be 2x squared minus 4x plus 2. but I'm multiplying everything by x. So that simplifies that just a little bit. So this will be 2x cubed minus 4x squared plus 2x. Now what I think I'm going to do over here is I am going to think of this expression right here as being negative 2 to the third times x minus 2. Sorry, that'd be x minus 1 to the third. That says the same thing. Regardless of what happens, I would still be able to factor out that negative 2 and raise everything to the third power. So this would be one way that I could look at it. The reason I'm going to do it that way is I think it's going to make it a little bit easier. This makes this negative 8 over 3 multiplied by x minus 1 to the third. And the reason this is simpler is because now I can take the antiderivative, or I can take the antiderivative much simpler than I could have before. I wouldn't have to deal with that chain or using a u substitution or anything. So remember, this is the moment with respect to the x-axis. And now I'm going to anti-differentiate this. So we get x to the fourth over 4 but times 2, so over 2, minus 4x cubed over 3 plus x squared. Now, the antiderivative of x minus 1 to the third is going to be x minus 1 to the fourth over 4, but I'm multiplying by 8 thirds, so I'm going to put this as minus 8 twelfths, x minus 1 to the fourth, evaluated from 0 to 1. And now when I substitute this in, my moment with respect to the x-axis is 1/2 minus 4 thirds plus 1 minus, well, that'll be minus 8 twelfths times 0. I don't know why I'm writing that. Minus, now plug in 0. Every other term is going to be 0 until we get to this negative 8 twelfths times 1. And so then my moment with respect to the x-axis, if I plug that all in or simplify, that would be 5/6. Okay, so there is my moment with respect to the x-axis. Now I'm going to repeat this process, but with respect to the y-axis. So go ahead and hit pause and try finding the moment with respect to the y-axis. Okay, let's try the moment with respect to the y-axis. It looks like it says my. So it would be from 0 to 1, 0 to negative 2x plus 2. That's not changing. I'm actually going to scoot this over just a little bit more. This time I'm going to multiply x times x plus y, that row function, still dy dx. So simplifying 0 to 1, 0 to negative 2x plus 2, we get x squared plus xy dy dx. Now I'm going to do the iterated integration, and I'm going to start with that inside integral. We're going to go up a degree, so times y, x squared would be treated as a constant, and up a degree divide by the degree, so we'd get xy squared over 2, evaluated from 0 to negative 2x plus 2. Remember, that's our y value, or those are our y values, I should say. Now, when I substitute in that negative 2x plus 2, we get x squared times negative 2x plus 2 plus x times negative 2x plus 2 squared over 2. And this first part we're just going to distribute in. So I get the integral from 0 to 1 of negative 2x cubed plus 2x squared. This second part right here we've actually seen before. We saw this over here, so I'm going to use that same, you could do the math, but I'm just going to use what we've already done. And we get 2x cubed minus 4x squared plus 2x dx. So the moment with respect to y, now I can, let's simplify it first actually. I notice that there's a fair amount that will cancel out. So when I do that, I end up with negative 2x squared plus 2x dx. And that's going to be a little bit easier to take that antiderivative of. So when we take the antiderivative here, we get negative 2x cubed over 3 plus x squared, evaluated from 0 to 1. And so we get, plugging in 1, we get negative 2/3 plus 1 minus 0 minus 0. So that's minus 0. So my moment with respect to y is 1/3. Okay, well, let's talk about what that means. I'm going to zoom out just a minute so I can fit this all on the page. Okay, what that means is my center of mass, the center of my mass, meaning the place where this particular mass or this particular lamina is balanced. If it were on a 1 point, somewhere in this region, where is this surface balanced? Well, my surface is going to be balanced at the ordered pair 5, 6, so that's my moment with respect to x divided by my mass, and 1/3 my moment with respect to y divided by its mass. Obviously, we wouldn't normally write that, but I just wanted you to see that I am doing the divided by mass. If we look at that in context of the problem, if I were to picture this surface floating up above this region, so I have this triangular region, and I take the surface that is just above this region, meaning the surface that is casting this shadow, and I were to balance it on a point somewhere so that the surface was completely level. That point that I'm balancing it on is that center of mass, is that 5/6, 1/3. 5/6, 1/3 is somewhere right in here. Really hard to tell on that tiny little diagram. But we can see that point, it would be in there. That is my center of mass. Okay, so the final application I want to look at actually has to do with the density as well, similar to our last example. However, this one is used in electricity, and it is referred to electric charge distributed over a region, or what we call the charge density. So the charge density in units of charge per area is usually given by a function sigma, which is this lowercase. So this lowercase Greek letter right here is the lowercase sigma, sigma of xy, and then the total charge is given by the double integral over the region D of sigma xy dA. So here's an example. Charge is distributed over the triangular region D in the figure below, and the charge density at any point xy is sigma of xy equals xy, measured in, I'm not actually sure how you say that unit, coulombs? Per square meter. I'm probably not going to repeat that because I don't actually know that that's correct. So find the total charge. Now the way this is set up, the first thing that we want to do is find our region or define our region. So if we look at our region here, and if I were to consider this in terms of dy dx, my region would be the y value, the lowest y value would be 1 minus x, and the highest y value would be 1. And if we consider then the x's, would go from 0 to 1. Or if I want to consider dx dy, and you get to choose, if I want to consider dx dy, the x values, the lowest x value is what I get when I solve this equation for x. So I would get x equals 1 minus y. So my lowest y value would be 1 minus y. I'm sorry, my lowest x value would be 1 minus y, and my highest would be 1. Then my y's would range from 0 to 1. So you get to choose whether you're going to do this with respect to x first or with respect to y first. And it really doesn't matter. I don't think there's going to be one that's going to be easier than the other in this case. But since the problem was given to us in y equals 1 minus x, I think I'm going to do dy dx. So I will set up this integral to be from 0 to 1 and from 1 minus x to 1 of xy dy dx. So we know that that sigma function is xy, so that's what we're plugging in. Now this just becomes an iterated integral. So go ahead and hit pause, try this integration, and see if you can't get the same answer I do. All right, when we take the integral of this, I'm going to get xy squared over 2, evaluated from 1 minus x to 1, and that will be in the integral of 0 to 1 dx. So evaluating this first part, we're going to get, let's substitute in 1, we get x over 2, and then substituting in the 1 minus x, we're going to get x times 1 minus x squared over 2, and then that is dx. Now I am going to simplify that just a little bit. Actually, you know what I'm going to do? I think I'm going to pull out the 1/2. So let's pull out the 1/2. That'll make it. So we get x times negative x times 1 minus x squared. If I FOIL that, I'm going to get 1 minus 2x plus x squared dx. And so we get 1/2 the integral from 0 to 1 of x minus x plus 2x squared. Oh my goodness, minus x cubed. Ignore this. This should be x squared and then parentheses. Okay, so minus x cubed dx. So combining like terms, we get 1/2 the integral of 0 to 1 of 2x squared minus x cubed dx. Now I'm going to evaluate this integral, and that is going to give me 1/2 times the integral of 2x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1. And so then I'm going to get 1/2 of 2/3 minus 1/4 multiplied by 1/2. So all of that is going to give me 5/24 when we simplify that down. So hopefully you found that the electrical charge, or the electrical density, the charge density, sorry, that's what I was looking for, is 5/24 measured in that unit per square meter. Okay, so you have a WebAssign assignment that goes along with this, and we will see you soon.